All right, let's just dive right in. We're going to talk about data structures and algorithms. And I know, for a lot of people, that's a pretty intimidating topic. But our goal here is to take it from something you might fear and turn it into a solid, powerful foundation for how you solve problems.
And look, let's just get this out of the way. If you hear a word like algorithm and you get a little pang of imposter syndrome, you are definitely not alone. It can feel like this secret knowledge that only certain people have, but I promise you, that's not the case. It's way more down to earth than you think. Because here's the big secret. An algorithm isn't some kind of magic. It's just a recipe. That's it. A set of instructions to get something done. I mean, your morning routine? That's an algorithm. The directions your GPS gives you, that's an algorithm. And here's the thing. If you've ever written a function, you've already written algorithms. You're doing it already. Okay, but not all recipes are the same, right? Some are way faster than others. So when we're talking about code, how do we actually measure speed? How do we even think about what makes one set of instructions better than another? Well, we use this tool called Big O notation. And yeah, it sounds really complicated and academic, but all it really does is help us talk about how our code's performance changes as we give it more and more stuff to work on. It's basically a way of looking at the worst case scenario so we can predict how our code will behave under pressure. And here's a really cool way to think about it. Just imagine different vehicles. Something that's O of 1, or constant time, that's like a rocket ship. It's just instantly fast, doesn't matter how far you're going. On the other end, you have O of n squared, quadratic time. That's like deciding to bike from New York to California. You'll get there eventually, but it's going to take a long time. Okay, so before our recipe, our algorithm, can do anything, we need to have our ingredients organized. And that's exactly where data structures come in. You can just think of them as different kinds of filing cabinets, each with its own unique way of storing and finding information. So the most common filing cabinet, the one we all use all the time, is an array. It just stores everything in a nice, neat row. Seriously, just picture your old high school lockers, all lined up one after another. If you know the locker number, or what we call the index, you can go right to it instantly. And this right here, this shows you the fundamental idea you're always going to run into: trade-offs. With an array, those lockers, you get that super fast O of 1 access. But with something called a linked list, which is kind of like a treasure hunt where each clue points to the next one, it's really easy to add or remove clues, but finding a specific one means you have to start at the beginning every time. Then there's something called a stack. This one's easy. It works exactly like a stack of pancakes. You can only put a new pancake on top, and you can only take a pancake off the top. The last one in is the first one out. Simple as that. And HashMap, you might also hear it called a dictionary, is like the world's most efficient code check. You give them your ticket, which is the key, and they instantly hand you back your code, the value. It makes looking stuff up unbelievably fast, usually that O of 1 rocket ship speed we talked about. So let's actually put this all together. How does our choice of filing cabinet, our data structure, end up affecting the recipe, the algorithm we have to use to solve a problem? Let's make this real. Imagine you've got a sorted list of 1,000 numbers. They're stored in an array. Your job is to find one particular number inside that list. Now, there are a couple of ways you could go about this. So the first strategy is the most obvious one. It's called a linear search. You start at the very first number and you check it. Is this it? No. Okay, check the next one. Is this it? No. And you just keep going, one by one, all the way down the line. So what's the worst that can happen? Well, if the number you're looking for is the very last one, or if it's not in the list at all, you have to do 1,000 checks, 1,000 operations. In Big O talk, that's ON, or linear time. It works, but it's not exactly elegant, is it? But wait a second. Remember that key piece of information we had? The list is sorted. That's a huge clue. We're not using that information at all. We can be way, way smarter here. This is where binary search comes in, and it's a total game changer. Instead of starting at the beginning, you jump straight to the middle of the list, and you ask one simple question. Is the number I'm looking for higher or lower than this one? And just like that, boom, you've just eliminated half of the list in a single step. You just keep doing that, cutting the problem in half, over and over again. So for our same list of 1,000 items, how many checks does this take? In the absolute worst case, just 10. From 1,000 down to 10. That is O log n, logarithmic time, and it is incredibly, incredibly fast. I mean, just look at that difference on the screen. It is not even a competition.
1,000 operations versus 10. This is the whole point. Choosing the right algorithm for the way your data is structured makes a world of difference. It's night and day. So, what this all really leads to is a huge insight. Learning this stuff isn't about memorizing lines of code. It's about developing a whole new way to think about problems. And there's a name for this skill. It's called algorithmic thinking. It's the ability to look at a big, messy problem, break it down into clean, distinct steps, and then, and this is the key part, identify which tool, which data structure and algorithm is the best fit for that job. And why should you care? Because this skill makes you a fundamentally better problem solver. It's the foundation of almost every app you use, from Google Search to your favorite video game. It helps you write code that doesn't just work, but that works efficiently and can handle growing bigger. And let's be real, it's a huge part of what top tech companies are looking for when they hire. So again, the big takeaway is not that you need to be able to perfectly code a binary search from memory at 3 a.m. That's not it. The goal is to understand the concepts, to know the trade-offs, to just know that, hey, I have a sorted list, I should probably be thinking about something better than just checking every single item one by one. So instead of a scary, abstract topic, you can hopefully now see this as a really practical toolkit, a toolkit for solving problems more effectively, whether it's in your code or, frankly, even in your day-to-day life. So I'll leave you with this. What problem are you going to break down first?